Okay, it seems I have a couple more examples to do with congruence integers, but we're probably all experts on this by now, so let's just get to this quickly. I don't think I did these. So let one. Another example. How's the quiz, by the way? Okay. How about this one? Yeah. So we're assuming A is equivalent to 5 mod 6 and B is equivalent to 3 mod 4, then what does that mean? A minus 5 is equal to 6x. It could be 0. What's just some integer? What about the other one? So b minus 3 would be equal to 4y. For some integers x and y. Okay? Then what can you say?
A is equal, yes, we can say what is A and what is B.
And so, well, now we just try to plug it in here. It seems to be the logical thing to do. So 4a plus 6b would actually be 4 times 5 plus 6x plus 6 times 3 plus 4y. And we're hoping this simplifies to something like 6 plus 8 times an integer. So this will be equal to plus 20 plus 24x plus 18 plus 24y. And so this would be equal to what?
38 Separate 38 into 6 and 32. Plus 6 plus 3.
6 plus?
That's 8 times 4 plus 3 times 4.
Can you just take out
I don't hear what you're saying. What are you saying?
6 plus 32
6 plus 32.
plus 24 times x plus 1. And then pull 8 out of the 32 to 24.
So we have 4 plus
3 times
3x plus 3y. Which of course means that 4a plus 6b is equivalent to the 6 here plus 8 times an integer. So it's 6 mod 8. look bad. How do you prove that the cube of an integer is always equivalent to itself mod 3?
So that means, so assume that a cubed is, I guess we're just trying to mess up. A cubed minus a equals 3 times.
So let a be an integer. Then, if we look at a cubed minus a, what can we do with that?
3 times x.
No, we can't say that.
And now what we're assuming? Or that's what we're trying to prove.
That's what we're trying to prove, right? So, assuming that this is 3x would be begging the question, which I should probably mention that at some point, what begging the question is. Yeah, so what would we try to do here? What can we do?
Trying to prove that A.
We want to prove that this is 3 times something. That's what we want to do. But how do we get there? So this would be a times a squared minus 1. What can we do with that?
Plus 1 and minus 1.
Alright, so this is going to be a minus 1 times a plus 1. And now what's your argument?
One of those numbers is going to be
Right.
3 months. That is going to be 0.
Since
not 3.
these are 3 consecutive integers, one of them is divisible.
It's a C in consecutive. That's what
Come again?
it's a C in consecutive. That's what you're.
You can see what?
It's a C in the middle of consecutive. That's what
Yeah, that's. Well, I'm like, something's not right.
That's what's right. The Q is
Right. Like, something's off here.
yeah.
This is. My brain shut down for a second. Say, nope, that's not right. Okay. Okay. So one of them is divisible by 3. Several ways to proceed here without loss of generality. Assume b minus 1 equals 3k. A cubed minus a is equal to 3k times a plus 1. That's not bad. You have 3 consecutive integers, one has to be divisible by 3. Right? And we know that by the division algorithm again. You can prove that by cases if you'd like, but that's that should be a somewhat obvious fact at this point. If you assume a is 3k, you're done. If you assume it's 3k plus 1, then this one would be 3k. If you assume it's 3k plus 2, then this one would be 3 times k plus 1. So by doing the cases, you can find that 1 will have to be divisible by 3 by going through all the possible cases of what a can be.
So if you had.
Yes.
I was just gonna, do we need to write the not loss of generality for this?
Yeah, because I said one of them is divisible by 3, but I don't know which. So I wouldn't want to say, hey, suppose this is divisible by 3. Now suppose that's divisible by 3. Now suppose that's divisible by 3. I'd essentially write down the same thing 3 times.
So it wouldn't be suffice if we just said one of them is divisible. It wouldn't be enough.
So,
Because isn't the question just asking if it's divisible by 3?
yeah, so because what I really want to do is to get us in the habit of like things looking like the definitions that we have, I really wanted to write this equals 3 times something. So that's why I did that. But yeah, in general, eventually we're going to get to a point. So like when I'm sure that you guys are really comfortable with proofs, like after chapter 7, then writing something like this part, I probably wouldn't care whether you wrote it or not. Like, you wrote up to here, then I'd be like, yeah, okay, he knows the rest of it. But right now, I just want to sort of hit home that the definitions are always what we want to go back to.
So, if you had started off with a cubed minus a equals 3 times something, and then shown that something had to be an integer.
How would you get to there? But in general,
I mean, you'd end up having to do like the same type of thing, but.
Yeah, in general, you couldn't do that. That would be called begging the question. And that is sort of equivalent to, because I remember someone was sort of doing this last time. So there are two main mistakes to avoid. One mistake that it can really creep up on you. I mean, we're not doing very complicated things, so it probably is easy for most of you to see it at this point. But there comes a time where it's a real danger to beg the question. Right? This is basically assuming what you want to prove. Right, so for example, starting the previous proof. Right, the proof right here as something like assume a cubed minus k. This equals 3 times k, and then working backwards. Find k is incorrect. It is begging the question. Right? What you're actually being asked to do is to prove that this can be written as 3 times an integer. So you cannot start your proof like that. That's called begging the question. Closely related to that is to prove P implies Q. Assuming Q and showing that is kind of what begging the question is actually. So it's like, you want to prove something, you want to get somewhere, but to start there and then work your way back is actually illegal, because doing that, what you're actually doing, there are times when it might seem to make sense, but it actually never makes sense. What happens here is that one would prove, what you actually prove is Q implies P directly. So begging the question is sort of like a direct proof of Q implies P, which we know is not equivalent to P implies Q. Right? Do the truth table for these two guys, you don't get the same thing. So it's actually never correct to sort of start where you want to be and then work your way backwards. It's actually logically, it's a logical fallacy. So just wanted to mention that, because the truth tables don't match up, so you actually can't do that. Okay, so those are all the examples I wanted to do on congruence of integers. Let's do a couple of examples on real numbers. I won't do a lot because, people are usually familiar with real numbers, work with them so much. Just to make sure, I asked this on, was it this quiz? I asked this on the last quiz. How do we define the absolute value of x? Right, it's x if x is greater than or equal to 0, and it gives you minus x if x is less than 0, right? That's the definition. That's the guy whose graphs looks like a V. So it likes to keep things non-negative, so whenever your x is less than 0, it takes the negative out of it to make it positive. Okay, so that's the absolute value of x. I'm going to prove what we call a lemma. Any real number x, it's not on, I didn't ask on this quiz, I think this was also one of the ones for the last quiz. We have, a real number is always less than or equal to its absolute value. Did anyone prove that last time? How would you prove that fact? By cases. What are the cases? Right, sort of to put up into cases of the definition. In case 1, what do we have? If x is greater than or equal to 0, then your absolute value x just equals x. And so x less than the absolute value of x holds, right? Because we have equality in that case. And in the other case, in case 2, if x is less than 0, then absolute value of x would just be minus x, which is greater than 0. So we have x, which is less than 0, but that's less than absolute value of x because that's greater than 0. And so x less than or equal to absolute value of x again equals. So that's the limit. For real numbers. What I want to do now is I want to do an alternate proof of the triangle inequality. I would probably need another lemma for you to be convinced by it. So in your textbook, they proved the triangle inequality, which I'm going to state pretty soon. But what they did was they did it by cases. Assume, 1 is less than 0, greater than 0, and all that. And they went through like 4 cases. So I actually want to do a proof where we don't need cases, but we're actually going to need lemmas. We're going to need to know, for example, this fact. And we're also going to need to know this other fact. So let me call this one lemma 1. Not terribly complicated facts. Lemma 2 is what I wanted to show. Let x and y be real numbers, then x is less than y if and only if x squared is less than y squared. In other words, squaring elements maintains the order of when they're bigger or small. For positive numbers. It actually won't work for negative numbers. And in the next section, we'll learn about counterexamples where you could easily actually prove that. So assume x and y are both positive numbers, then squaring them maintains their order. How would you prove it?
You have to prove
Proof direct.
Okay, you want to do this way first? All right.
Yeah.
So assume directly x is less than or equal to y, then
Square both sides by x and then square both sides by y.
well, you can't square both sides.
I mean,
That's
sorry, not square, but like multiply both sides by x.
multiply both sides by x. So I can say this means x times x is less than or equal to x times y. X is positive, so we can, when we multiply an inequality by it, it doesn't change the way the inequality turns.
And then also multiply.
And so this here is x squared less than or equal to x times y, which we actually know is less than or equal to y times y, because I know that x is less than y. So if I replace x by something bigger, I get a bigger expression, which is y squared. Okay. And now let's go the other way. What if we know the squares have a certain order? How do we know we can actually just take the square root of both sides, the positive square roots, and not worry about it?
Should we just do the contrapositive?
You can do the contrapositive. So assume
y is less than
x is greater than y.
same thing.
Then x squared would be greater than xy. And since x is greater than y, this is greater than y times y equals y squared. So we have that one. This wouldn't actually be that bad to prove directly, by the way. If you started here, just bring things to one side, factor them by difference of two squares, and you can get to the answer that way. But yeah, so we have these two lemmas, two roughly elementary facts. You should have come across them already in your calculus classes, so they shouldn't be that bad. So now, want to prove the triangle inequality, which is a very, very important inequality. We use it all the time, all over the place to prove random things. It's called the triangle inequality. If x, y are real numbers, then anyone know what the triangle inequality says?
Absolute value of x plus the absolute value of y is greater than or equal to the absolute value of x plus 1.
Right. When you sort of distribute the absolute value function, you actually get something larger than the original. This is called the triangle inequality. A lot of times you'll see people who write this shorthand, they actually draw a triangle and write something like ini. That's short for the triangle inequality. So your book actually goes through this and they did various cases. So they're like, what if x and y are both positive? What if this is positive, that's negative? What if this is positive, that's negative? What if both are negative? And they went through the 4 cases. I think 2 of them are covered by without loss of generality. And they actually proved it that way. I actually want to do a different proof. And it's actually also a common proof. I think your book just wanted to use the definitions again. But it's very common to see a proof like this, which we're actually skipping, which you have to know these two 11s to know it works. So what it does is it uses this stuff. Knowing about the square can get you to something without the square. So what you actually do is you start with the square of the absolute value. It turned out that this is actually the same as just squaring a number, right? Because squaring makes everything positive, not positive anyway. And so now we can start to expand. And this is actually still equal to this. It's an elementary fact. How do you think we get to where we want to get to?
Square the right side. Up the inequality.
What about the inequality?
Square the right side as well, the inequality. Up down.
How am I going to square this?
No, up the absolute value, that's the absolute value.
Oh, you want to start on this side and then square it and sure you can get the same thing?
Well, I was gonna say you square them and then you can compare the two absolute value x times absolute value y and show that it.
Yeah, how do you know you can replace this with absolute value x, absolute value y? And what would that give you? Something bigger or smaller?
Okay, by cases.
You don't need cases. You have this, right? I can literally just say this is going to be less than or equal to that by lambda 1. Right? If I replace x with absolute value x and y with absolute value y, I get something that's bigger. Right? So I just did that. But this would now, I can just foil it. That's actually that. And so now what I have is this squared is less than or equal to that squared, but this just means the inside, x plus y, is less than or equal to x plus y by lemma t. Right? I can literally just drop the squares and the inequality sign will actually remain in the same direction. So this is actually just one very short computational proof of the triangle inequality. And it uses these two lemmas. So it's just an alternative way to think about proving things like this, other than the way the book did it. In a similar fashion, we can prove something called the reverse triangle inequality. Which says if x, y are real numbers, then when you throw subtraction into the triangle inequality. I think that the absolute value should be on the outside. Some people don't. Yeah. How do you prove this one?
Using the triangle inequality.
Okay, how?
Say x equals x minus y and y, or sorry. Say, so since the triangle inequality says, a, absolute value of a plus b is less than or equal to absolute value of a plus the absolute value of b, say a equals x minus y, b equals y, and plug it in, and what you get.
Okay, yeah, all right. So I see what you're saying. Usually how they do it is they say something like this, where you have the x minus y and the y, what you're talking about. you can start like this, and then they do something like you subtract y and you add y, right? And then they look at that as, think of this as the A, and think of that as your B, right? And so the triangle inequality is going to tell us that this is less than or equal to x minus y plus y.
Subtract y, absolute y.
Okay, so what is the problem here though?
That one has an absolute value sign.
This one has an absolute value sign, that one doesn't. So how do we fix that?
Well, the absolute value of something is always going to be less than or equal to. Oh wait, no.
No. The absolute value of this guy is going to be bigger than this guy.
Yeah.
How do we know it's not bigger than this guy also? How do we know it fits in between?
Well, if you take the absolute value of both sides, you take a double absolute value.
You take a double absolute value. Would that work all the time though? I feel like there'd be cases where that would be wrong. Because remember, you're subtracting here. So this side could be negative.
Yeah.
Could it be a larger negative than that is a positive? So it turns out I probably wouldn't have proved this way. If this was what you wanted to prove, then yeah, that would be a great way to do it. So, how would you actually do it?
Try squaring it.
Go back to what we know worked, right? If we take x minus y squared, we know that this is just x minus y squared, which is equal to x squared minus 2xy plus y squared. This is of course equal to x squared minus 2xy plus y squared. And how do the inequality go now? If I replace this guy by absolute value x, absolute value y, which way does the inequality point? Which expression is bigger?
That's the smaller than.
This way would be the one that works, right? Because here we're subtracting a positive number. So this, we're subtracting something bigger than we were before. And this would just be x minus y all squared, which is actually equal to we can call that lemma 2. And this is again by lemma 1. Triangle inequality and the reverse triangle inequality are actually pretty important. They show up all the time. Let's see. And actually to prove this on the quiz, I believe, on the last quiz. On this quiz. Alright. Let's see. So we have two more sections in this to cover. We're going to do proofs involving sets and then Cartesian products of sets. And next time we're going to cover proof by contradiction, which is really cool. How to prove something by proving its opposite. Well, a statement involving its opposite. Which is why being able to negate a logical statement is important. Let's actually do this one. Give me the definition for these, as concisely as you can. What's the union of two sets?
X is an element of A, or X is an element or all X.
It's a set of all X such that X is in A or X is in B. Of course, inclusive or intersection.
X is in A
And X is in B. Here, set of all X such that
and X is in A.
and X is not in B. That is the definitions. Okay, so let's prove a claim using sets so we can see what that's like. Because sets also show up all the time in mathematics, so we need to know how to prove things involving sets, not just numbers. Let's do an example. A claim. A intersect B is equal to this is one of the Morgan's laws for sets. Sets X and Y.
What's MB set?
Huh?
What's that MB?
Oh, note. Note. It's an abbreviation of a French word that means note. What must you show to prove that two sets X and Y are equal? They're subsets of each other. So we must show that X is a subset of Y and Y is a subset of X. And by the way, X is a subset of Y means
X is an element, or if little x is an element of big
if
X,
X is in X, then
X is
X is in Y. Okay. Alright. So with that in mind, how do you prove that?
Well, first write down what it means to be in each side.
Which way you want to do first? So again, we have to do two things. Let's show this is a subset of that and this is a subset of that. Which one do you want to try first? We first show A intersect B complement is a subset of A, B, and B. Alright, so what do we do? Let X be in A intersect B complement. I need to show that X is in this set. How do I do that?
So then write down what that means in terms of those original sets A and B.
Right. Then X is, what can I say? If I know it's in the complement of A intersect B, what can I say?
So it's
No, it's
not in A or it's not in B.
Yeah.
How do you get to that? How do you get to or?
Take the negation of that, right?
Well, hold on.
Oh,
Let's,
yeah.
let me remind you what A complement means. What does A complement mean? If X is in A complement, what does that mean?
Not in A.
So that X is not in A. That's the definition, right? Of course, here we're assuming X is in the universal set, but X is not in A. Right? There's always this overarching universal set. Okay, so X is in the complement of this. What does that mean?
So it means that X is not in A and
X is not in the intersection. But that means, if it's not in the intersection, what does that mean?
But it's not in A or.
It's not in either of them. X is not in A, and X is not in B.
But that,
But it can be.
but it can be an A or B because it's the intersection, not B.
Yeah.
How could it be in A or B?
Because if it's not in the
It's
intersection.
never in A, and it's never in B.
But there are elements that are in A that are not in the intersection of A and B. And vice versa. Right?
Okay, so what?
Like if we look at the Venn diagram, you can have things that are in A that are not in the intersection.
So you're saying, what if the guy is like out here?
Yeah. And it will still be, that will be in the complement of the intersection.
Okay, so how do we deal with these cases?
So replace and with or.
Is that good? Yes. Okay, so that's why we have to put an or, because you have to worry about these guys here, right? What if it's in A but it's not in B? It wouldn't be an intersection, but what if it's B, it's not in A, right? So that's where the or comes in, right? It's to deal with the situation where we're in either this area or this area, right? And so this means if X is not in A or X is not in B, then
Then X is in the union of.
The X is a complement of.
then X is in the complement of A or it's in the complement of B, right? Then, well, this is just a definition of the union, right? So this means X is in the union of the complements. So that proves one direction. Now let's go the other way. To show that this is a subset of that, assume X is in this guy. Then
Pretty much just work backwards.
right. So then X is in the complement of A or X is in the complement of B, which means X is not in A or X is not in B, which would mean X is not in both at the same time, which would mean X is in so for sets, to prove equality, you sort of have to prove two directions all the time. So it's kind of like this if and only if thing where they don't have to state it. So it's one thing you have to always be aware of. For sets, equality means proving inclusion in both directions. We'll end there. We'll cover some more examples with sets and then Cartesian products of sets next time and move on to proofs by contradiction. The solution for this quiz is already on the website, so you can check that out and get a chance. And CD1